Yeah, all right. Hello, ladies and gentlemen. And today we're going to talk about positional encodings and long context. And Tamerlan is going to present. Finally, it's not me. Yay, hooray. So I'm dropping off my video, and I'm wondering if I need to share any kind of permissions with you to.
No, I think I'm good.
Yeah, lovely. All right. Mic is yours.
Yeah, we'll talk about positional embeddings today. Mostly, we'll talk a bit about some attention tricks, but I think we'll talk more about them next time as well, because there are a lot of things to explore there as well. And was too deeply absorbed into this topic. Yeah, so positional encoding transformers. We all know the general gist that transformers attention doesn't see any positions. Every like sequence of tokens for him is basically a bag of words, which, as we discussed a bit last time, isn't actually true, and we will discuss it more later. Yeah, but in original paper, attentional need, they um, opted to add some positional embeddings, encodings that will basically act as a watermark for a position for each token. Yeah, we all know like this picture. So mm, each token has its unique watermark for the position that it sits in. Like this is like for the first token, this is like for tokens that are far away, and we can see that they're actually pretty similar for uh, no, this is for tokens far away, yeah. Um, and one of the very first things that people tried after that was just ditching this concept entirely and applying like uh, directly some penalties on long distance tokens. So we all know that usually when we generate a token, we want to look at just tokens beside it. And the basic idea of this paper, which is called alibi, is just to apply directly apply a coefficient in softmax that punishes attention for tokens that are far away from the current token. Yeah. And then came the rope. We all know how rope works. We divide our dimensions into blocks of two. These blocks of two represent vectors in two-dimensional space, and we rotate them by different frequencies. But apart from everything that we know, rope actually has some interesting properties which are useful in training, but also kind of detrimental, and that other approaches try to solve. Let's look at one of these properties, and it's like the main one. So they give this formula for rope in the book. Yeah, and we basically all our lower dimensions they change their angle very frequently with the position, and higher dimensions change the angle very slowly with the position. And if we take just two vectors of ones and apply positional embeddings rope like with exactly this formula to them, and just vary the distance between them and look at their attention score between them, then we see that rope actually does what alibi does by itself. So it has higher attention score for close tokens. Like this x is, sorry for not labeling the axis. So x-axis is distance, relative distance between tokens, and y-axis is attention score. And we see that actually we have already automatically, we are looking at close tokens with better attention. This is all good, and this is a useful property, but it is also detrimental because if we want to go for really long contexts that are like higher than 1,000, we can see that it like very fastly decays with relative positions. And like mostly that's okay, but sometimes when we generate a token, we need to look like very far back, for example. And that's a problem that ABF tries to solve. Uh, ABF stands for adjusted base frequency. And they basically say, let's just increase the base frequency, and this will, as we will see now, make this more flat. Yeah, so I've actually have this exact formula here, but where we can look at different parameters. So B is our base frequency, which is usually by default set to 10,000. Uh, let's, yeah. Yeah. And x-axis is again like relative distance between tokens. And this is attention score, but I normalized it to one this time, so we don't have to always adjust the scale. And yeah, and we can see that if we increase the base frequency, so this decaying becomes less. Yeah, and this is all good, but this kind of decay helps us with short context, and this helps us with long context. So what they do in the paper is they so they first train with normal rope without this extended uh, base frequency, and later when they go into continual pre-training and they increase the context size, they adjust this base frequency and make this decay smaller. And this can be viewed in another way, that we're actually like interpolating our positions. So the position that was the relative position of like 1,000 previously becomes what was relative position of 500 basically. So we can trick. Let me actually mm, show you a picture. I think there was a nice picture of general positional interpolation. Yeah, like this. Uh, so imagine this is how our angle in some frequency fluctuates in rope. And with linear interpolation, we can just squish this distribution and squish this graph and make it so our model thinks that it's at a different relative position for which it knows how to work. So we initially trained like on 2K tokens, then we want to inference, for example, on 4K tokens. We just squish that at 4K tokens. The model thinks that it thinks what it thought when it was on 2K tokens in training. And this linear interpolation, we just literally changing indexes, so distances become smaller. But with ABF, we are changing base frequency, which kind of makes the same, but like the distribution is different because we are changing small frequencies a lot and high frequencies not that much, or vice versa. I don't remember exactly. But the point is, it's non-linear. Um, yeah, this is the basic idea, and usually we pre-train on, and they say this in the book, we pre-train on relatively small sequences. Mm, yeah, because we still want to have good quality on like low length inputs, and we save some computing data with this. And only during continuous pre-training, later in the training, we or what we also call fine tuning, but that's a separate thing. We apply this ABF and train a bit more so the model can readjust. Yeah. Is everything clear for now? I assume that's a yes. Mm, yeah. Yarn, which does talk about, mm, says that, yeah, that's all good, but we actually have another problem. And let's look at this problem here. So, yeah, this is again, x-axis is our relative distance, and y-axis is cosine of an angle that our token was rotated for. And K is like what dimension we are looking at. Let's suppose we are training on like at most 1000 tokens. And for dimension of like 1, 2, 3, we actually see all the values of this angle during training. Like mm, the whole frequency is completely inside our training range. But as we go into higher dimensions and have lower frequencies, we see that we don't actually see this line being like lower than 0.5. So we don't see this angle all the way to 360 degrees during training. And then when we go to longer sequences, then it becomes something else, and we are basically out of our distribution. And this is where ABF helps because say we only trained to 500 and this was the only like position where we saw something and we didn't see any of like these values. We can just let me yes, and then when we train on 1000, we have this out of distribution value. And when we increase our base frequency, basically bring this value into our distribution, which was about this line. Yeah, and this is all good. This is what ABF works well with. Yeah, the problem is in, like as I say, the problem is in these high frequency things. This stuff helps the model basically as they work as absolute position medics. Now, scary that I'm not sure about that. That shouldn't be true. But for high frequencies, we don't actually need to change them at all with our ABF because they already work all right. We don't have any out of distribution values here. We just change them and the model becomes confused even if we train. We just like make it harder for the model. So the main thing that they do in Yarn is exactly this. They just let me find out. Yeah, that's what I just said. Yeah, they only change base frequency for dimensions that suffer from the problems that we need to bring into distribution. So only for frequencies like this, we do apply the base frequency modulation. But for frequencies like this, we just don't do anything. And this is what this formula says. Yeah. That's all good. Oh yeah, one more interesting thing with this young stuff, and they also say is like when we infer models in our like regular distributions, when we start inferring, we don't actually need to adjust anything. We can just infer as we were inferring before without ABF and anything because we saw that length. And only when we start going into like these more extreme lengths, we can start applying this. ABF, and also we can just apply it for the length that we need, and that works. And I was initially skeptical because like wouldn't this just ruin KV cache fully? But they actually talk about this, and you can just since rope we apply as we I think talked last time. I think here we have a good picture. So, well, since we apply rope just in attention and not everywhere, we can just save all KV tokens before we apply rope and cache them that way, and then apply rope after we get them out of the cache each time. Yeah, and this thing actually works even without post-training because like we basically do regular inference. We just apply it. We just apply this hack when we go into long context. So we degrade slowly. We don't like lose all our quality right away. And that's nice. But like you still need to continually pre-train if you want to get some good results. But that works. And it's funny because they in the paper uh, they say yeah, this idea was actually proposed by a Reddit user in local llama. Uh, so and we came to the same idea, and like people in local communities actually like do a lot of stuff to improve their networks without, and if you can do it without consumer training, that's very, very nice for them. um, yeah. Altogether, it's actually a very simple picture. We have standard rope, we can adjust its Bay frequency, we can interpolate positions linearly as we saw here. You can do basically ABF but with smart number. Uh, these are just basically the same thing, but here we have a specific number of frequency that we want to adjust to. And yarn is ABF, but only for some of the dimensions. And they're all very similar, but they do help to generalize to longer sequences, either with training or without further training, and increase model size, model context length. Yeah. But then, sorry, came an idea, and I feel like with LLMs, when we like scale and like see new stuff every year several times, we always need to reevaluate all the concepts that we saw earlier, because like, what if we don't need this hack anymore? And it's also very hard because you don't actually know beforehand what will really affect the final training. Like you can do all the ablations, but if you can not change something and you're not sure it's better, you won't like just drop it away. You will just keep it because it works. Which they also talk later about in the book about like Adam and Muon optimizers, because it's hard to test stuff. Yeah. So and yeah, one of the submissions was, what if we just don't use Nope at all? Don't use rope at all and just throw it away, and will the network actually learn? And it actually does learn, and it's strange because we always thought that no, we like the attention doesn't know anything about positions, but it actually does. I think you discussed a bit last time. I think you actually like did everything correct by the formulas as like they uh, write in the paper. But yeah, so what they found is you can actually have no positional embeddings, and it generalizes better than uh, than the regular positional embeddings, but they usually, and that's what they say in like later papers, they usually perform worse on short contexts, but they generalize better to long contexts. So there's a trade-off. And with this trade-off, we can easily come to an idea that what if we just do sometimes rope, sometimes no rope. And yeah, that's exactly what they are suggesting in the Smol training playbook. And I had this paper open somewhere. Maybe not. Oh yeah, in AirNope, they drop drop visualization weightings in some layers and keep them in others, and this gets you best of both worlds. You have good quality, and they show it in their oblations. Good quality on small tasks, small context tasks, and you potentially don't lose quality on long context tasks, but they say here that like you have regular needle in a haystack, where where work where rope works okay, but on like harder benchmarks like Lurie and Hammett, and as far as I understand and as I saw, these are benchmarks which are not just like find something in a long text, but like take this long text and solve this problem that uh, checks if you actually read all of it and remember all of it. Yeah, but they don't actually test, I think, the their model on these things, but as far as I understand, that's because you can't. You need to train the whole model and then do continual pre-training if you want to get like proper results on these ablations. And so they only check on like the same benchmarks that they had before, and they say that, well, using nope, which is like error nope actually, when we alternate between nope and rope, doesn't hurt on small tasks, then it will probably help on long context tasks, and therefore we'll keep it. Yeah, as that's what I take from like their experiments here. And I think there was yeah, let's talk a bit about how does attention actually uh, how do networks actually understand the positions, and we are talking a bit about it a bit. So uh, and don't know where the red is actually. Okay. Mm, so yeah, we have our causal inference, and when we our current token can only look at the previous tokens. And suppose we have some previous tokens and we have some attention in them, and suppose the network can make all attention scores equal mm, for all previous tokens. Then when we softmax them, we'll see like this picture, yeah, for like for softmax attention scores. Like the first token will see like one full score. The second token will see two half scores. The third token will no. You see what I mean? The second token will see one full score. The third token will see two half scores. The fourth token will see three third uh, scores, and so on. And if you make the model, but that like doesn't really help us because again the model doesn't know which of them is first, which of them is second, and their position because they are just summed in the network. But if we can make a layer or like a small part of our hidden state such that for beginning of sentence token, which we don't always have, but we'll talk about that. If it always outputs one and all other tokens output zero when we like attempt them, then we will have something like this. And this now, well, not zero, but like very low values before. So, and this from this we can actually infer our current position because like we can just inverse the sniper and networks can do this, and we will get the position of the current token by looking at previous tokens and how many of them we see, basically. Yeah, and then from this we can infer relative positions, but the problem is we don't actually have beginning of sentence tokens always, especially with this document chunking. We usually separate documents by a special token, but it might not be in our current batch as far as I understand. And but what they argue in the paper is you usually have some tokens that go in the beginning, like prompt tokens, like hello worlds, stuff like that, and the network can use them to infer current position. Like, and if this happens like in lower layers, then it can propagate and become stronger in uh, later layers. Yeah. Then comes the drop, which is yeah also um, an attempt to take best of both worlds, but in a more sequential way. They first train with, I think we maybe looked at that. Yeah, they first train with rope because rope trains better. Uh, we have loss that drops faster. And then we like drop our rope entirely, go with nope, and of course our loss rises dramatically, but then after not a lot of steps of training, it drops back to lower values that nope is on the current stage. I'm just like playing the plot here. Yeah. So this is uh, another way to get most of most roles because like we saw in another paper for nope that nope is better at generalizing, but we saw that rope is better at short context task and in general training. This one gets us supposedly better generalization because nope, and better training because we trained with rope initially. Yeah. Uh, yeah, that's it for positional embeddings. Mm, the next thing that we will be talking about is mm, yeah, maybe we'll discuss this a bit as well. Um, is attention techniques for like, extending our scope, extending our limiting scope to extend our context size, and also to save on compute, but that's a separate topic. Um, but to be honest, I didn't like prepare thoroughly to this part, but I don't think there are, well, I think there are a lot of stuff probably if we go deep into the, but the general idea is, yeah, with chunk attention, we just divide our sequences into chunks, and in each chunk, we can only attend uh, to tokens in this chunk, in the same chunk. This is obviously like quite bad because like this AIDS token can't attend to anything else, to anything before it. So the model suddenly loses all understanding of what happened previously. Yeah, I think it's all right when you go deeper, but still. Uh, the other, um, I think this is like the most popular technique right now, sliding window attention, where you just attend to like n previous tokens before, and we also like forget something. But you can actually, and you must actually also keep some of the initial tokens. So you basically, as you go through inference, you remove tokens from your KV cache, and this is like great for several reasons. First of all, you don't have long context problems. Secondly, you don't your attention is easier to compute. But of course, you it's bad because you don't see what was in the beginning, and you can keep this beginning stuff, and you must because they found when applying these techniques, they found that when you start doing windowing, the quality drops significantly. And I think. Mm, yeah, they showed it here. Uh, so with dense attention, we obviously uh, our perplexity rises dramatically when we go out of our with regular attention without all the tricks that we discussed out of our pre-training lengths. With KV with window attention, which is same window attention, we the perplexity suddenly rises when we like start doing the windowing when we run out of our Kiwi cache. And yeah, and they found that this happens because the model uses these initial tokens as attention sinks, and basically, if it doesn't want to attend to anything, it just dumps all the attention in the initial tokens. That's part of the reason, also because like initial tokens are important, yeah. But also sometimes model doesn't want to look at anything, and we don't really have a mechanism for this in attention. And this is why people now, I think everyone now use attention things. There are actually two methods of doing this. You can either do an off by one attention, where you just add one to the denominator of softmax, because with this one, you actually have a scale to the thing, and the network can just make all the weights, all the results very low, and due to this one, the actual attention scores will be low. And Mm. Yeah, or you can just like make a separate place for the network to dump its attention to that's not connected to the input tokens and like that doesn't carry any meaning apart from being a sink for attention. And if you do this with sliding window attention, or if you just keep the first tokens, then this problem disappears, and you don't have this sudden rise in loss when you go out of Kiwi cache size. What is- Yeah, and I think that's like what they do in streaming LLM. Mm, yeah, and that's basically it from me for today. We also have dual chunk attention, which I like understood last week but forgot by this one, and I want to understand better. And I think we also wanted to discuss paper by someone in the chat about like why rope embeddings don't really work as we expect them to. And I think we still should do this. And I wanted to prepare it by this day, but I think I will probably drop it into chat as a like separate note on like short information about how does this work and what they come up with in the paper. Yeah, so I think next time we'll probably talk a bit more about attention techniques, and yeah, that's it. We can also discuss a bit how rope is works with MLA, like what how it doesn't. Uh, but then again, yeah, this no, this picture doesn't sum it up very well because I had to go through this with Gemini, I think, later on. Mm, but the general idea is when we when we're doing latent attention, the whole uh, savings that we have is because we can pre-compute two matrices, which are WQ, I think, and WC. We can pre-multiply them and mm, beforehand, and we don't actually need to unembed the latents into actual K and V's. Uh, yeah, no, no, should Q's, right? Uh, Q and K, I think. And when we add rope to these matrices, we actually can't do this because rope is different for each position, and we can't pre-compute position agnostic like this. Yeah. So when we do MLA, we don't use ropes and heads that use MLA. Split by rope and no rope. Uh, yeah, I think that's everything from me for today. Mm.
Right, awesome, awesome. Thank you very much for presenting. And well, Andrei, do you have any questions? Because I don't.
No, I don't.
Well, right then,
Okay.
yeah. Thank you for the presentation, and I guess well, I'll follow up separately in the chat about next week whether we have a presentation or not. So
Mhm.
staying in touch, guys. And
Yeah.
this is the end of the recording.